All right, I think we're good. Make sure my mic's on. We got an excellent group in the teams here. So we'll get things going here. All right, hopefully people on the thing can see me up there. I'm Seth with McDonald Miller. We got some people in the room here. This is great. Welcome. We're going to kick off with the intro to HVAC. I'm going to be in the back running the Teams thing, so if you guys have questions on the remote, you can type it into the chat, and we will. I'll ask the instructors here. So we got some classes coming up in addition to this one here. This is Intro to HVAC Part 1. So this is intro. This is the beginning of the series. And we have some other classes coming up here. Next month we have Part 2, and that'll include more of your bigger systems. We're starting with kind of the smaller systems now. Next month is going to be VRF. We're going to get into hydronic heat pumps, some of the bigger multi-zone systems, and so on. So we're going to start pretty small with today's presentation. This is not a new offering. We've done customer education for a few years now at McDonald Miller. And this time, what's different about this year is we're doing it in our Redmond office, Everett, Seattle, and Tacoma, and also down in Oregon. So it's kind of a neat offering. And then we offer the teams for those of you that are outside the Seattle area. So thanks for being here. Appreciate your time and effort. Our instructors today are downtown Seattle technicians from what we call Zone 1, Joe Brethauer and Brian Skeleton. And they're new to instructing. They are, what? Skeleton? Skeleton? Yeah. Skeleton. Okay, I said skeleton. It's skeleton. Very close. I apologize. They're new to this, so they're kind of figuring this out too. It's a kind of a learning curve for everybody. It's a growth opportunity. So without any further ado, I'm going to turn it over to those guys, and they're going to lead us through objectives in the class.
Cool. All right.
Thank you, Joe.
Thank you, sir. Cool. So I'm just going to start off. Every class I've ever been to has a little intro. I'm Joe Brethauer, like you said. I work downtown Seattle. I've been doing HVAC for about 7 years now. My first 3 years were in residential, so like going to people's crawl spaces and all that kind of fun stuff. The last 4 years have been commercial with McDonald Miller. So I kind of wanted to go around and just see maybe what your guys' names are, so you're not strangers, and then maybe what your experience level is or what you know. So you want to go first, Brian?
Yeah, my name is Brian Skeleton. I'm in a similar boat as Joe. I started in the residential side of things, did a few years of that. Again, attics, crawl spaces, all that fun stuff. Once I got tired of that, I decided to move over to the big leagues here in the union commercial side, and I've been with Mac Miller for about 3 years now. So.
Yeah. Start with you.
I'm Antone. Right now I'm working with Kara Matthews, but I used to work HVAC for 2 years. I was just an apprentice, so I didn't get to finish my apprenticeship, but now I changed careers.
Is that commercial or?
Yeah, it was commercial.
Cool. Nice. Awesome.
I'm Katie. I work here also at McDonald Miller. I work in workplace services as a corporate services coordinator.
Oh, cool.
So I don't know that much about actual HVAC stuff,
yeah.
but I did like Mac business and stuff, so I know like a little bit.
Cool.
I also work in workplace services. I'm the front desk admin up at the upper building.
Sweet.
So, yeah, also kind of in the same boat. Don't know a ton about HVAC.
Awesome. Well, cool. It's good to have you guys here. So kind of with the class, here's the things that we're going to touch on. There's going to be a little bit more. Feel free to ask questions as we go. It goes by really quick if nobody has questions, so please feel free to ask. We might even get to a lot of it while we're going through. But we'll start from zoomed out, how HVAC systems are selected from like an engineering standpoint or even the customer with the engineer, basic design considerations. We'll talk about a central plant system versus a unitary system. We'll talk about package units versus split systems. We'll go over a little bit about like building envelopes that gets thrown around a lot now, and then we'll talk about a little bit on filtration. And a lot of this stuff, like he was going over with the classes, we'll have whole classes about just one. This really is just kind of scratching the surface. All right, so the first thing we're going to talk about is like when systems are selected. So when buildings are built, the engineers and the customer have a goal in mind of what they want to accomplish. If it's like a hotel, they probably want something that's quiet. The people staying the night there aren't going to notice that it's running. If you're running like a lab space or manufacturing, they have standards like super strict air quality standards and really strict building pressure standards. Like for example, in operating rooms, they have to be in a positive pressure so that dust can't come into them and infect people while they're operating on them and do that. So one of the biggest things that you'll find as a building engineer, if you're inside of a space where, let's say, the use case has changed since it's been built. Like I've got some office spaces that a lab moved into and has retrofitted half the space to be a lab and half is still an office, but they still have the original equipment. And so there's a lot of conflicts there where you'll run into the equipment not doing what they want the use case now. So it's good to know what your building was designed for and take that into account. When you do go down to deciding what equipment you want, you can really only choose 2 out of 3 on this list. Quality, fast schedule, or low cost. This tattoo is just a funny way of showing you someone wanted a fast schedule and a low cost tattoo. So they got an ugly Freddie Mercury tattoo, right? So if you want quality, you're going to pay for it, right?
Right. All right, so the point of this slide is just to kind of touch base on some of our more common terms that we run across in the HVAC world, right? So some words you'll see thrown around are going to be BTU, which stands for British Thermal Unit. That's, in a nutshell, an easy way to think about what BTU is. It's the heat equivalent of 1 matchstick. So you light a match, the heat that it produces is the equivalent of 1 BTU there. Some other ones that we'll touch base on are tons. So we see 1 ton thrown around a lot. You look at a system, average house with HVAC in it is about 3 tons of cooling and 80,000 BTUs of heating. So what is 1 ton? Anybody know?
Is that the amount of pressure in the refrigerant?
So what 1 ton is it is a measurement of heat content. So if we look here, 1 ton is roughly equivalent to 12,000 BTUs. So when you say we have about a 3-ton AC system on our house, 3 times 12 is about 36,000 BTUs. So an easy way for us to convey that in a quicker way is just to say 3 tons.
How about HVAC?
HVAC, okay, yeah.
Yeah, you gotta, yeah.
So,
bonus question.
So, has there ever been a point in time where someone has mentioned the term HVAC and you had no idea what they're talking about?
8 years ago when I didn't do it.
Yeah.
Yeah.
Before I got into this trade, I had no idea what it was. And I quickly realized that nobody else that ever touches this has any idea what HVAC means. I get friends and family that ask me what I do for a living, and I tell them I work in HVAC, and I get that blank nod, oh, yeah, okay, cool. But yeah, HVAC stands for heating, ventilation, and air conditioning. There is another letter usually you may see happen after that, and that would be an R, and that stands for refrigeration. Refrigeration is just another form of cooling.
We should talk about where a ton came from.
All right. So design criteria. So this is a lot of information. I'm not going to go through it all. I don't expect you guys to retain it all. My main focus here is just to touch base on what is in the yellow box or green, whatever that color is. So when these buildings downtown are made, right? And I know Joe's talking about people have goals in mind. They have things they're trying to get out of a building, purpose built, right? There's also an efficiency, a design criteria that we're trying to reach here. So if we look here, oh, lost it. There we go. There we go. If we look here for outdoor design conditions, during the summer, say we're looking at 83, our design criteria here for this area is going to be to maintain a 75-degree interior space. On the flip side, for heating, during the winter, we design our buildings to maintain a 70-degree temperature inside our space at outside temperatures down as low as 24 degrees. Now that's a baseline. We can design for more extremes. I will say, you work for Kidder. Have you had any during the recent weather where your systems just didn't keep up when it was
Oh,
really,
yeah.
really hot?
Definitely. It was more so, when we had the snow, everyone was turning their heat on and, our system just couldn't handle it.
Yep, yeah. And that's not necessarily, there's anything wrong with the system. The problem is it's just too cold. It's
Yeah,
outside of.
everyone's ramping up the heat.
Exactly. So, so when we're talking about design conditions and sizing it that way, why do we think we don't shoot for the stars and design for our extremes? You know, why are we not sizing a heating system so when it's 5 degrees out, we're maintaining 75 degrees inside the space?
You don't need it.
You don't need it?
You need it.
Right. For most of the year, for the majority, that's not an issue, right? The biggest reason is cost, right? So if we're saying, say you have a house, right, and you have a 80,000 BTU furnace, and it does fantastic down to 24 degrees. Below 24 degrees, it starts to get a little chilly. It can't maintain that 70 degrees inside the space, right? Well, one option is to up it, right? Get rid of the 80,000, let's go with 120,000. Problem is, for the majority of the year, that's not necessary. And where the trade-off is on that is the cost to operate and maintain a 120,000 BTU furnace is going to be much more than an 80,000 BTU furnace. So something to think about there. While we're talking about maintaining temperature inside of a space, this here is a nice, cozy office space. Let's talk about cooling it for a second. What are some things you guys think affect a room's ability to maintain temperature with it? So think about this room right here. What in here is going to generate heat? Lights? Projector. Equipment. Yeah.
Us.
My hot coffee.
Us, yeah, exactly. So all of these things are what we refer to as a heat load. So it is generating heat within a space that our air conditioning systems have to overcome in order to maintain our temperature. What about outside? If it's really cold outside, is that going to make it harder to heat a space? What about cool a space? It's colder outside. Is that going to negatively affect our ability to cool a space? No. What if it's hot, like 115 degrees outside? Yeah. So that's what we call a heat load as well. It's just on the outside. So heat by nature likes to move from hot to cold. So if it's 115 degrees outside and we're trying to keep it 75 degrees inside our space, that heat wants in. And so when we talk about designing towards our extremes, that's something we have to account for. How often do we have 115 degree days?
More and more every year.
More and more every year, right? But not very often.
Yeah.
The problem is, when it does happen, it is uncomfortable, right? A lot of nuisance calls, systems can't keep up. However, for the majority of the year, that's not an issue, right? So let's talk about, I know Joe was talking about repurposing a building or having a purpose-built system, right? So let's say we have a nice 3-ton unit for this space here, and it's maintaining temp, and this is a nice, we'll call it a storage closet, right? Well, what if we decide, well, we now need this space to be a server room. So we're going to bring in a lot of equipment. That's going to generate much more heat load on a space, right? So suddenly that 3-ton system that was able to maintain that temperature, no longer able to keep up, right? So just something else to think about if you ever decide you're trying to repurpose a space. Something to think about is to contemplate what kind of heat load changes are going to happen within that space, and do we need to make any changes to the existing HVAC system to maintain it?
Yeah. Take over. Thanks, man. Cool. So you'll hear the term zone thrown around. Like you'll say, oh, my zone's too hot, too cold. Basically, what a zone is, it's an area where there's a thermostat. Like our thermostat for this room is on the wall over there. This is one zone. In this picture here, this is going to show you our actual building. in an issue that we have with this, and you probably run into this all the time, where they'll have one piece of equipment that controls multiple rooms, but because you only have one thermostat in one room, this is the only zone that equipment cares about. It's gonna, if this thermostat is set to 70 degrees, it'll run till this thermostat is 70 degrees in this room, but these other, like the hallway and coordination, it's gonna be whatever temperature it is. It's just, they get what they get. That's a really common one, especially for office spaces where you'll have one unit that serves multiple, and especially when you do like a TI project and now you subdivide offices, but it's still, or they don't add a supply grill to another one. You'll end up running into those issues. Our dream state when we talk about zones is that everywhere where you care about the temperature, where there's someone, everyone has their preference of what temperature they want it, you would ideally have, a piece of equipment that has a thermostat in each of those rooms, trying to run and control each room to the temperature that it wants. So as a building engineer, I'm sure you've had to tell people like, hey, look, the thermostat's not in your space.
Yeah, it's,
it is what it is.
well, it's like.
In so many words, yeah.
Yeah.
Yeah. Do you guys have any questions on zones? No?
What are some other options that you could do in that rather than spending money on on putting 3 systems in?
Yeah, so that's a good point, actually. So the thermostat we have in here, and like a lot of modern thermostats, they'll come with like remote sensors on them. We call those averaging sensors, and it basically you'll put a little Bluetooth sensor in each of those rooms. And what that allows it to do is run until the average of each room temp is met. So that doesn't solve your issue, but it does make it a little bit better because now you're taking into account each room. I've had a lot of those situations where, oh, do you want to spend $100,000 and completely install new stuff, or do we want to make the best of what we've got here and add some, sensors? Any other options than that without just adding new equipment? Suppose you can look at airflow balancing. Sometimes if the rooms have changed their use and they were designed, like when these rooms were installed, each of these registers here, when he talks about the CFM, cubic feet per minute of air, each one was designed to output a certain amount that keeps this room to the design conditions. Well, if we just subdivide the room and start changing the use case, maybe that changed, but they never went back and rebalanced the air to redistribute the amount of heating and cooling. So there's a lot you can do to make the best with what you got, up to a point. Is there anything else you were thinking about, Steph?
No, yeah, just kind of zone, like air balance is a good first step, although
Yeah.
it's not going to solve that problem.
No.
Sometimes you can add some other zone type control systems, but ultimately those are 3 different areas and 3 different uses.
Yep. So, yeah, on the topic of thermostats, here you go. We'll dive into these a little bit more.
So, Joe just talked a lot of jargon about thermostats. Does everybody know what a thermostat is? For the most part, everyone have one in their homes. Is it everybody turn it on when it's cold, or turn it on when it's cold and turn it off when it's hot? Yeah. What about scheduling? Does anybody know what a schedule is? So yeah, so thermostat in a nutshell, it's your interface to tell your HVAC system that it's too hot or it's too cold and we want it a certain temp, right? So this is your gateway to control. So some basic functions are going to be, it turns on the fan, right? We need air circulation, especially if we have people inside the space. Turns on the heat. Again, it's cold in here, bump it up, right? Turns on the cooling. Man, it's 90 degrees outside. I want it 74. It's 78. Let's kick on that cooling. The biggest thing, I think, is that it can manage a schedule. And this is going to be the majority of our more modern thermostats, digital. There may be some old mercury bulb thermostats, some slide thermostats out there. Unfortunately, you're still stuck with the turn it up for on and turn it down for off type thing. But what a schedule does for us is, at least in my opinion, and what I argue to my wife when we turn everything down at night, is it makes things cheaper. Especially for the commercial side. So say on a commercial building, office space, it's occupied from the hours of 7 to 5, right? Before that, nobody's in the building. After that, nobody's in the building. That's Monday through Friday. On Sunday, Saturday, Sunday, nobody's even in the space, right? So why would we pay money to have our HVAC system work longer to maintain temperatures, to keep people comfortable that aren't in the space, right? So that's what it does. So if we look here on most commercial thermostats here, we get two options, occupied and unoccupied, right? So on occupied, it kicks our fan on, it keeps it circulating throughout the day, opens our outside air dampers. That's going to allow fresh air into the space. It's going to give us our fresh air exchanges and make sure that everything's staying circulated. We don't get that stagnant air feel inside the space. Unoccupied, it says, well, there's nobody in the space. I don't need to keep this fan running 24 hours a day. I'm going to turn it off unless we have a call for heating or cooling. It also closes the outside air dampers because we don't need fresh air. And if it's colder outside, that heat's going to be running more often if it's pulling in outside air that's 35 degrees in the space. Usually they have two options that you'll see mostly, 5 and 2 or 7 day. 7 day means I can go in and change the individual schedule for every single day of the week. 5 and 2 kind of groups them together. So it's saying Monday through Friday, you can set one schedule, it blankets it. Saturday and Sunday, that's another one, single schedule, blankets it. Not only does this help reduce cost, it also helps our equipment, right? So the less our equipment runs, the less wear and tear it has on it. The longer the operating life, the less repairs have to be done, less maintenance costs, etc. So when we talk about how room temperature is controlled, again, going back to the slide thermostat, you set it at 70 and that's what it maintains, right? But say we have a heating and a cooling system, right? Well, we want them both to kick on. Are we putting it for 72 degrees and saying, I want this thing to maintain exactly 72 degrees? No. We have a gap there, right? So when we look at, I mean, even this guy back here, the Ecobee, will have heating set for 70 degrees, which means if our temperature drops below 70, it'll kick on our heat. Cooling, 74. If it goes above 74 degrees, it tells the system, hey, we need to kick on a cooling, bring that temperature back down. So why do you think there's a gap? Like, why would there not be a gap? Why wouldn't we just say, I want 72 degrees. If it gets below that, turn on the heat. If it gets above that, turn on the cooling. Any ideas?
Is wasting more energy trying to keep it exactly at 72 instead of having to,
Yes, right? So what happens is, our systems run a lot more frequently than we want them to. Again, that increases the wear on them, right? Most of your wear that happens to your equipment happens when it starts, right? It's trying to, especially a compressor, especially a heat pump, AC, when it's trying to get things moving from a completely stopped position, that's where we see the most wear. So the amount of times that we can reduce that thing firing off and on, the more life we're going to get out of that system, the less repairs we're going to have to make over the life. The other thing is we don't want them to fight each other. If you have them cycling back and forth, a lot of the equipment that I see, they have minimum run times, which means that if it gets above 72 and your AC turns on, well, it's not going to turn off once it gets to the lower end of 72. It's got a minimum amount of time it's got to run. And so that's going to cause what we call temperature swings. So it's going to kick on, it's going to run it 71, 70, maybe even lower. And then as soon as that's done, the system says, well, now it's too cold, let's kick on the heat. And that's going to cause it to be uncomfortable for us, and we want to avoid that as much as possible. And for those of you who were interested, that's called a deadband. Do they call it something else now? I thought they were moving away from that term. Seth?
I think it's just a deadband.
Offset, sometimes in controls, or sometimes they'll call it like actual or calculated set point, depending on the type of control system. But offset becomes pretty common.
Is that the new one? All right, touch base on system selection and their applications. Joe?
Cool. All right, next exciting slide. And there's some thermostats kicking around here too, if you guys want to take a look at them.
I think some of them are battery powered, so.
Cool. Later, guys. Thanks for swinging by. Cool. So this is going to kind of just get into identifying equipment. I'll stand over here so I'm not blocking you. So a lot of system setups, you'll see either central plant or unitary, or sorry, I should say you will have central plant and unitary in a commercial space. Basically what that means is, like, let's take this high rise here. The central plant portion of it is the boilers and chillers and everything located up on the roof or down in the basement that are going to be doing the bulk heating or cooling, whatever your heat transfer medium is, whether it's air or water. So let's say let's say a chilled water loop for cooling. It wants to maintain, let's just pick, I don't know, 55-degree water, let's say that. So all that work is being done by the large equipment up on the roof or down in the basement, and then you have water lines that go throughout the building that'll go to smaller systems that would be considered unitary, and we'll have another slide that shows exactly that. But basically your central plant does the bulk of the heating and cooling and delivers that heat transfer medium, whether it's water or air, into the building to the smaller systems inside. At your house, you'd have what's called a unitary system. It runs and basically controls a zone. Your house would be the zone with your one thermostat. This will make a lot more sense on the upcoming slides we'll show you. Do you have a question on that?
Yeah, is residential, like, most of the time unitary, and commercial is most of the time central?
Yeah. Yep. And actually commercial will have a combination of the two, and I'll show you exactly how that is. And then another definition, kind of splitting up types of units that you'll hear, is a split system versus a package unit. Do you have package units at any of your sites, the big units on the roof?
Yeah, we have a couple, and we've got a couple splits.
Couple splits. Okay, so yeah, you know the difference. But the way I describe it and the way I think about it is kind of a laptop versus a desktop.
Yeah.
A laptop would be kind of the package unit. Everything, you get it, it's ready to go, you plug your power cord in, fires right off, and you're off to the races. A desktop, you've got the desktop computer sitting down here, you got to run all these cords up to a monitor, you got to plug in a keyboard, you have to do a lot of the setup and add all these like extra accessories to make it run. And there are pros and cons to each, and why you would pick each one is kind of going to depend back on that system selection that we were talking about earlier. What's your goal? Can you have ductwork in the space? Do you have a roof to set the package unit on? Yeah, so a lot of that will depend on those factors there. But this will just show a basic picture. This would be like a normal house with a furnace in the attic, a system on the outside, and this is a split system. And there's wiring and refrigerant lines that have to connect the two. And then there's ductwork that goes into the house. And then this is going to be your package unit. And it does a pretty good job of showing you all the components, all included inside that package unit. I like working on these a lot more, honestly, just because everything's right there and I don't got to walk across the building or go downstairs and keep running back and forth. Everything's right there. I'm sure you probably like working on these more too.
For sure.
Yeah. Cool. So here's another picture of a package unit getting set. And some of the pros on it. I'll just go through mine. What are my favorites? The nicest thing, honestly, is that everything is right there. I don't have to keep running down to the indoor unit to check the filter or check if everything's running. Don't have to keep getting in someone's way or setting up asking them to move their chair to, get up in the ceiling and access the indoor unit. Everything's right there. And when breakdowns happen, like let's say a refrigerant leak happens and I have to find where is this leaking from and repair it. Oh my God, it's a lot easier to do it inside of a system like this than it is to go chase down 150 feet of line set that's going through a crawl space or through an attic, through the wall.
Drywall.
Yeah, through the drywall. That's the
Down
annoying
the
one.
shakes.
Yeah. Some of the cons, they are more expensive up front. You got to have a crane come drop it off. They don't make as many of them, from my understanding, so it's another reason they're going to be a little bit more expensive. And then another con is it's just sitting there on your roof. It might not be the most aesthetically pleasing thing to some people. But yeah, like it a lot. Yep. Did you have any more questions like package units or splits? Yeah, you can probably work with those a lot. Does anyone in the chat have questions on that?
There was a question about economizing. Why run a condenser if it's cold out?
Oh, yeah, you wouldn't want to. If we have free cooling available, cold outside air, it's really good to have the ability to just open up a damper and let in outside air and run a fan to cool the space, then kicking on a compressor. And gosh, if it's cold outside, you'd have to have low ambient controls because they aren't designed to run when it's 50 degrees outside. So yeah, there's a lot of benefit to that, mainly energy savings. Actually, a lot of money saved on that. So that's pretty much the benefit.
Yeah. Well, particularly with package units is,
Oh yeah, it's a lot easier.
if it has it, usually it already has it installed. If not, it's available from the manufacturer. You can throw it right on this box, right? Whereas with a split system, if we want to economize, I actually came from maintenance on a site today where we did just that. We had to run all new ductwork from the indoor unit, the furnace, to the outdoor to give them the ability to economize. Because there's a server room that they have in there that they like to cool 24/7, 365. They wanted to add an economizing ability to their system, so we had to add the ductwork after the fact. So, so he covered the pros and cons of a package unit. I'll touch base on a split system again. What I've seen, what I like, what I don't like. Pro, easy to conceal. That is true. So if you look at a package unit is everything, right? It's got the indoor unit and the outdoor unit all smashed together. Downside of that, it's bigger, right? Your average condenser is going to be about half the size, if not smaller. Makes it easier to fit outside. Not only easier to conceal, easier to fit. So if roof space is an issue, if you got a lot of other things that have to go onto that roof, you may need something a little bit more flexible space-wise than having a package unit sitting on a roof curb. You may want to look at a split system that's a little bit smaller footprint. Higher efficiencies. So package units, they're really hard to mess up. They come pre-spec'd from the factory, pre-set up. So the only limitation from that front is the ductwork it's sitting on, right? That being said, the average efficiency that we see from a package unit is between about 13 to 18 SEER, which, do you know what SEER stands for? That's okay. It's very uncommon. I have to refresh. SEER is the seasonal energy efficiency ratio. Pretty much the higher, the better. So about 13 to 18 is on average for your package unit. When we talk about a split system, we have split systems still can be within that range, but we can get up to 20 plus SEER. I think the highest is 25 right now available. So operational wise, they're much more efficient.
More readily available too. Yeah.
More readily available. Yeah, they're less expensive, right? Houses use these in droves. They are much more mass produced from the manufacturer. They're cheaper. Installing them, also cheaper. They're smaller. I don't need a crane to lift this thing on. I don't need permits to shut down the street, that kind of thing. So usually less expensive to install and maintain. Maintenance access. Again, I came from residential. In Tacoma, almost all of the systems are in crawl spaces. And they're not nice, lofty, big crawls. They're belly crawls that have all kinds of critters and stuff down there. So maintenance access on those things are usually pretty rough. In the commercial side, we'll usually see things like these stuck up in a T-grid in a drop ceiling. Access, ideally, if this space was completely open and there were no desks, people, chairs, anything like that, I could put my ladder wherever I want and get up in there. Not usually the case, though, in most places. So that becomes its own
You're pretty
challenge.
good on a ladder, right?
Yeah, really fast.
Working safely, right?
Definitely not on the top row.
Install issues, again, package unit, crane pulls the old one off. All you gotta do is put the new one on the right way. Don't duct the supply to the return, right? So we do run into issues, especially if it's a new install. If we've got to find where we're taking this copper line set, these refrigerant lines, and running them to connect our indoor and outdoor unit, that can create a whole new set of problems.
Yeah.
And again, takes up space inside. A package unit, it's on your roof. If you don't care about what's on your roof and people seeing what's on your roof, that's the way to go. Split systems, as great as they are, you do have to find a spot for them inside your space. So if you're limited on interior space, that may be something to take into account, something we need to explore options on. Oh boy.
Yeah.
So these are all split systems. These are all the outdoor units. So these are all the condenser sides of the split systems. So I know I was talking about a smaller footprint, but when you multiply them by that many, it's still quite a sight. So over here we have what we would consider our smaller side discharge. These are going to usually be your little mini splits. If you have a little wall mount unit that's mounted on the wall and just has a fan motor from there, usually they're tied to these guys here. Usually that's 1 to 2 spaces for the most part for those systems. So if we're trying to take care of an entire building as they are using that method, you'll get something like this. You got to account for getting rid of that heat somewhere, right? Down here is going to be our more traditional. So if you have a system at your home, this is usually what you're going to see mounted to the side of the home there. Just a traditional, nice condenser. Great to work on, terrible to change a compressor on. There's nothing quite like hanging over the top, trying to pull a compressor out through the top of the system. This guy in the top right corner here, these are the condensers for what we call VRF systems. Think of those as souped up mini splits. They are fantastic.
I like that.
For what they can do operational wise and efficiency wise, but they have their own set of issues and design criteria as well that has to be taken into account. And that's something that we'll touch base on during the next class more in depth. Boom, heat pumps.
Oh, sweet.
All right. So do you know what a heat pump is?
Yeah.
Yep, it's some people say reverse cycle air conditioning. But one of the big things, and especially around here, we're a great climate for a heat pump. And the reason for that is even when it's 40 degrees outside, there's still heat content in the air that we can pull from. With air conditioning, we are pulling heat from your 70-degree home, taking it outside and just kicking it out there. We don't care about it. We can reverse that operation with a couple other components and actually pull heat from the outdoor air and bring it inside. So one thing to take into account though with heat pumps is that the colder it gets and the less heat content there is, their capacity will start going down and decrease. Let's see, some other things you'll find with a heat pump, especially around here, is you'll have some form of like auxiliary heat or backup heat. Usually it's like electric strip heat that'll turn on when it gets too cold. Did you have any issues with this? I mean, do you have heat pumps in a lot of your buildings? Any of these like split systems?
I haven't done heat pumps as much with Cater, but I did a lot of heat pumps with my HVAC company.
Okay, yeah. So a lot of the issues are maybe the changeover set point wasn't set up. Like I'd run into this in residential. If I was installing a heat pump with electric heat, you'd have to find that point where, okay, when is the heat pump not keeping up, and when should I just turn on the electric heat? Switch over or turn it on to supplement. So there are some different controls and things you need to take into account with that. But really the point of this whole thing is just to wrap your mind around the fact that when it's cold outside, we can still pull heat from the cold outside air. Even, we think it's cold, but there's heat in it, and we can utilize that and heat your space with it. And the reason you would do that instead of just, well, why wouldn't you just use electric strip heat? Well, it's usually 4.5 times more efficient to run a heat pump than it would be to run that electric strip heat. If you've ever lived, like I've lived in an old house in Seattle that had just baseboard heat, and my bill would literally be like $450 a month for heat. A 1940s house with no insulation, it was miserable. So the heat pump would have been nice. I'd be a lot richer today, if I had it. So.
How much more efficient is a heat pump than electric heat?
Well, that'll start dropping off the colder it gets outside, but usually it's about 4.5 times, right? It's typically.
Depends on the COP.
Depends on the efficiency of the unit you're getting, but then you can go into VRF systems or inverter driven that'll ramp up and down and do all these other things that get way more efficient. But just your basic run of the line heat pump, from my understanding, it's about 4.5 times more efficient, just right next to electric heat. Is there anything you wanted to add to that?
Nope.
Cool. All right, so now we're going to talk more about the package units here. We're going back to the gas pack. Let's see. Yeah, basically just showing you in a little bit more detail. I like this picture more just because we're going to show you, like when people are talking about the economizer, have you had to deal with economizers, Matt? Yeah, so in a gas pack, that's easy. I'd open this side panel and it's right here. Here's our access to outside air that'll come in. You can also have a relief fan here for when your space starts overpressurizing, which that's the next couple slides to talk about that building envelope and pressures and all that. But yeah, you can see everything's just right there. You have your evaporator coil, there's your heat package, there's the fan with the belt, your filters are going to go in here, there's our condenser section with the compressor. Like you can see why that'd be a lot easier to do repairs on as far as like a refrigerant leak or changing out a TXV. Like everything's just open. I can take the lid off that and just get to it. So that's why I speak so fondly of my favorite. You see anything wrong on this picture?
Is that hood upside down?
No, what we're trying to point out is, I don't know if you see this lovely peach wrap here.
Yeah, what is going on there?
I don't know what they were doing with that one. I think Seth, you had a theory, right?
Yeah, it's a little shallow for a condensate trap. It looks like maybe it wasn't glued and it swung down.
Yeah.
That's what I'm thinking. I'm thinking it just
Oh,
flopped
that
Yeah.
makes so much more sense.
Yeah, we actually noticed that after we put the picture up here. Everyone in the field's like, what the hell's going on with this thing? Yeah. But this is when we're talking about, this is what you're going to see on the roof. For a commercial space, I mean, most people probably don't care. They're not really going to look at it. But like, I'd have a hard time telling, my partner that we're going to put that on our roof.
Yeah.
Right? Like, that's probably not happening. So, or in the side yard or in the backyard. Yeah, yeah.
Oh, the house.
Yeah.
Yeah.
You see those though. I mean, yeah, I see them.
Some places in the country, yeah, they love package units.
I would do that, but like, yeah, even in, when you talk about space consideration in Seattle, you have to maintain, what was it, 36 inches from like the property line?
Yeah.
It's like a ridiculous amount when you set your outdoor unit. It's even for a regular system, it's hard to get that because people want to put it on the side of the house and then you're blocking the walkway. You can't walk on the side. So like, yeah. Anyways, that's a tangent, but one of the things to think about. All right, so Brian's going to talk about building envelopes.
Envelopes.
Envelopes?
Envelopes. All right, so building envelopes. What is it? Has this been brought up to you before?
Never heard of it.
So an envelope, pretty on the nose. Think of it as the separation from the inside of your space to what's going on outside, right? So there's usually, rarely ever will we find neutral, but when we talk about interior pressure within a space, you'll hear that thrown around. There's usually two. There's either positive pressure or negative pressure. Positive pressure is when we are bringing more air into the space than we're exhausting out of the building. Negative, reverse, right? Which one do you think we want? No, we want positive. And the reason for that is that we want to control where that air is coming from. If we're negative, pressure is always trying to reach equilibrium, right? So if we have more pressure outside than inside, that outside air wants to come in and fill that gap. And it will. No building's 100% sealed, right? And what happens is when we bring that air in, we can't control where it's coming in from. It's going to come in under that door, from the walls, from our outlets, from the ceiling, anywhere it can. What happens is we can't control that air. So if it's cold, we can't temper that air before it enters the space, which means we have to heat that up, right? The bigger thing is dirty. We're pulling it from a wall cavity to come in and equalize the pressure inside this room. I don't want to think about what's inside that wall cavity. Whereas positive, right? If we're bringing in more air, the air in here is trying to escape, which means we're not pulling anything in. We're actually trying to get rid of it. And what that means is that the air that we are bringing in, we can control that. We can pass it through our filtration. We can temper it before it enters the building, right? And make up air.
We have a question from Janice,
Yeah.
but I don't know how to unmute her. She has to unmute herself or ask in the chat.
Okay.
But if she unmutes, she can ask in the room here.
Is it possible to ask a question at a, no?
Yeah,
Absolutely.
On the previous picture on the package unit, there are 2 sets of coils, correct, that need to be cleaned? Evaporator?
Yep.
Could you show me where those 2 sets of coils are?
Yep. So this is your evaporator or your indoor coil. So in cooling, this is going to get cold. In heating, it's going to get warm. And then your
I
outdoor
can't see
coil.
what you're pointing to.
Yeah, I'm trying to get the camera over there. See if I can, I don't know that I have a way to do that. Let me see here. See if I can find a picture for her. Maybe you could use your pointer on your PowerPoint. Down the lower left-hand corner, there's a little button there to turn your pointer on.
Laser pointer tool.
Oh, yes, perfect. I can see your pointer. Yes. Where are the
Sweet. Yep. Yeah, so this here is our evaporator. This is our indoor coil.
Uh-huh.
And then the other coil you're talking about is our outdoor coil. That's this orange or red guy right here on the right side of the system. And this is what is going to be exhausting our heat.
Kind of point over on the real picture there too with the pointer.
Oh, yeah. So our outdoor coil is going to be right here on the right side. And then our indoor coil is actually going to be right about here, right next to where our filters are, but before our fan motor.
So are the out, okay, the one on the right side, that
Yep.
exhaust coils, do they need to be cleaned frequently and easily? Are they cleaned? And the other one by the filter?
Yeah, so they should see routine cleaning. The frequency really kind of depends on the environment that they're in and the amount of usage they get. If the system's not running as frequently and we're not pulling air through that coil, it may not get as dirty as if it was running more frequently. And then again, it's the environment. We have some places where we're next to a lot of cottonwood, or there's a lot of road debris that gets pulled into the coils, so they get dirtier more frequently. Really, in order to assess that, we'd have to go out there and just kind of monitor it and see what happens throughout the year, and from there we can kind of determine what frequency we would need to clean those coils to keep them running properly for you.
Is it correct to say that evaporator coils are harder to clean and cleaned less than the condenser?
Usually, and the reason why they may be cleaned less is usually because we have some form of filtration that sits between them and the incoming airflow to filter out a lot of that debris, whereas our outdoor coils are just open to the environment. As far as access, they can be, especially depending on some of the equipment where it's located and the design of the system. On gas packs or package units like this, usually access is pretty easy. We usually just open up the door, the side panel there, and we get a pretty unobstructed access to those coils.
Is that one, the coils by the filter is easy to clean, correct?
On a package unit, yeah, for the most part.
Okay, the second question, from under that unit, you're going to have ductwork, and ductwork needs to be cleaned. And the so when somebody's up on a rooftop and they're going to be, a duct cleaner is not a good HVAC person. They're going to be coming in from the top, and they're going to have to be careful of that. What is it, economizer, correct? They can damage things.
Sure.
I mean, yeah, it's possible. Usually when we look at duct cleaning, usually we find some way of isolating our coils and everything above that ductwork line from the rest of the system. Not only so we don't potentially damage it, but so we don't bring that dust and accidentally pull it into that coil, right? Because that's just going to lead to more cleaning necessary. But yeah, for duct cleaning, more often than not, you're going to be looking more on the return side because that's going to be pre-filtration. And so you're just pulling in whatever's inside your room. It's going up into that ductwork and it's not getting filtered. So usually if you're looking at a system, your return duct is going to be the one that gets dirtier. But again, for cleaning, you're absolutely right. It is possible to do damage if proper care is not taken. And again, usually there's some form of isolation on that duct from the package unit to prevent such things.
So you were saying the coils on the right side, the pulling air out of the room are the ones that will be dirty if you have a dirty tenant.
On the
Dirty air.
left side, yeah.
Yeah, okay. Okay, and possibly both sides would need to be cleaned. Tenant can cause the one and the other is just the air outside from, say, ships blowing their sacks and so forth, cars, anything. So one's inside,
Yep.
one's outside, air. Okay, I got it. Thank you.
Yep. Of course.
That's helpful. Thank you.
Of course. Glad to help. Alrighty, so positive and negative air pressure. On this slide, on the left here, let's go ahead and get this here. There we go. Here we have a little bit of cause and effect here, and this is going to be an example of negative. I know we were talking about pulling air in from wall cavities. So what this is over here is this is someone's ductwork down in their crawl space. You couldn't tell by that lovely insulation job there. Actually quite roomy. I would be happy to have that crawl space, right? What's happened here is that this flex duct, what we call flexible ductwork, has come off of the rest of our ductwork here. So what's happening is we're making our crawl space more, really making the critters happy down there. But what's happening is that we're no longer bringing in as much air into our space as we're pulling out. So this, what's that? Probably about an 8-inch. So say we have a 3-ton system, which is roughly about 1,200 CFM or cubic feet per minute of air. Say we lose this guy to the crawl space. Well, our air handler inside is trying to reach equilibrium. It's trying to pull in as much air as it's pushing out, right? It doesn't matter where it goes, it's still going to try and pull in as much as it's pushing out. So what happens if we lose this duct, say we lose 300 CFM out of our 1,200 CFM out of our space, so we're pulling 1,200 out, we're only putting 900 into our home. What's going to happen is it's going to go negative, right? We're pulling more than we're putting in. It's going to try and make up that air somewhere. If we're only getting 900 from our conditioned air available, the air that we can control, the return side of our system is going to pull the other 300 from wherever it can get it. Again, under doors, or in this case, from our walls. I don't know if you have white carpet. My in-laws have white carpet. I am vehemently against white carpet for this fact. If you do have white carpet and you walk the border of that carpet and you see a dark ring around the edge of this carpet in any space, that's dirt and debris and dust from your wall cavities. That means that your building's in a negative, it's pulling air from your wall cavity, the dirt is getting caught in your carpet fibers and it's coming in, which means you're breathing that in, right? So we want to prevent that. So obviously this is something that needs to be fixed, addressed. You need to get that building into a positive. So how do we do that, right? Here's a kind of an animated example of an office space. We have, looks like 2 office spaces on the left side. On the bottom here, we can see they're in a nice positive. On the left side here, we have a kitchen. Maybe some fish being cooked there. And it's in a huge negative, right? Why might that be desirable? Why would we want our kitchen with this smoking fish in a negative?
Smoking fish.
It's a good image.
Yeah. smells, right? We're trying to reach equilibrium. If this kitchen is in a positive, more so than these spaces, that air is going to try and go to the lower pressure, which means it's going to carry that smell with it. So what we have here is an exhaust fan that's working overtime to try and contain that. It's trying to keep that space into a negative to keep that smell from escaping. It's trying to get it out of this building, not spread it from that space to others. As far as maintaining positive pressure within a space here, you can see here we have an air handler, so obviously some kind of split system. We're pulling in outside air here on the left. That's coming in our return. It's pushing air out through our supply, down into our spaces. These two office spaces have returns in them. They're pulling air back up, coming back, and then it's getting pulled into the air handler and mixing in with our outside air. Again, we want that fresh air getting pulled in. We want those fresh air exchanges. We have a relief here, and that's to prevent overpressurization of our space. We like positive pressure. We don't like too much pressure. We don't want the doors on the front of our supermall getting blown open when you tap on it, right? The reason for that is we're losing money. We don't want to heat the outside, right? We don't want to cool the outside. We just want to make sure that we're not pulling in anything from outside. Any questions on that? Seth?
Yeah, I had been called in, they said, so air don't creep.
So air does, that's exactly it.
So air don't creep.
Well, you want that pressure, that's because positive pressure always goes to negative, so you always get that flow.
Yeah, we don't want to break room bandit.
You don't want going backwards.
No.
Oh, I was gonna say too, with this, this is another thing where when we were talking about how buildings are, like the airflow is designed, we have a certain amount of air that comes out of these vents and then a certain amount that returns. Like in a lot of the lab spaces I'll work in sometimes, they have to maintain a positive pressure. So I mean, like our test and balance department goes out and they have to say, 400 CFM in, 370 CFM out, where they have to measure it and like make sure each of those spaces are pressurized. So if you have a space that's depressurizing or used to work but isn't, a lot of times a damper might fail, it might not open when it should have. So that's a common one that like you might have come across too of dampers fail, stuff like that. So building pressure is huge, and the more you get into it, the more you run into pressure issues. So.
On a side note, in a tangent here, talking about pressures in a home and dirty carpets. Let's talk about some common ways that we can fix that or identify why that's happening. So that duct is an extreme for that carpet. That carpet can populate and you can crawl from end to end in that crawl space and not find any ductwork that's disconnected, dropped, open, anything. In homes nowadays, every room's got a supply, right? So whether that's in the ceiling, in the floor, most modern homes, you'll have 1 to 2 along the perimeter of your home, usually by a window. Do you see returns in those rooms? And does every room have a return that has a supply? No. Builders got cheap. They didn't want to run twice the ductwork, right? So usually an average home has 1 to 2 returns, but every room within that home will have a supply. So the quickest way to bring a space inside a home into a negative is you close your doors, right? If your return is in your hallway, in your living room, in the main space, and you close off all the doors to your bedrooms, those bedrooms are great. They're super positive, right? You're only pushing air into there. You're not returning anything. The problem is that air is not coming back to that return. So then your main space becomes a negative, right? So quick way to remedy our dirty carpet is if you can't open the doors, leave them open. There's gaps under our doors for a reason. That way, when those doors are closed, we're still getting that air exchange from room to room. So as great as those under door insulators are, they do cause their own set of problems. And then supply vents. I know nobody ever closes off supply registers, right? It doesn't get too hot in a bathroom, so you close that down, right? That also affects the amount of air you're bringing into a home. So again, your system's trying to pull air in, it's trying to push air out. You close that off, the air is gonna go somewhere, right? may not be into that space, but what happens when you close off half of your supplies is that you're no longer bringing in the same volume of air into your home as you're pulling out through the exhaust. So that's something we should be doing, but probably won't, is open our supplies. And then one last thing on building envelopes, I think, yeah, is controlling that positive pressure, mainly at entryways, right? Usually we see two methods here, especially on the commercial side. It's the revolving doors, which I've gotten caught in those before, so I know they say to use those and not the side door. I'm terrible at that. I still go through the side door. The other one is the air curtain, which I think is much funner. If you've ever gone into a grocery store or something and you walk through that nice, powerful beam of hot air as you walk through, that's an air curtain. And what it's trying to do is it's creating a barrier. It's keeping dust, debris, bugs outside. It's preventing it from coming inside, and it's also helping to prevent that positive pressure from escaping through an open door. Same thing with the revolving door. It's creating a seal to help prevent pressure loss through our entry and still allow people in and out of those buildings. So. Filters.
All right, exciting part.
The most exciting part.
Yeah.
You maintenance.
Cool. All right, yeah, I'm sure you deal with filters a lot, especially with COVID. You know, everyone wants to go to the highest MERV that they can possibly get to.
You guys.
Yeah, exactly. Yeah, everyone wanted to upgrade their filters. Some common rules of thumb, you'll see 1-inch, 2-inch, and 4-inch filters is kind of what you're showing here. Kind of one of the main service calls I would take in residential, though, believe it or not, would be not only people didn't know, you know, what filter, they don't know they have a filter, but a lot of times they would stack up like 4 1-inch filters to make a 4-inch filter. Can't do that. A lot of people may already know that, but if you didn't, 4 1-inch filters does not equal 1 4-inch filter. That's way too much air restriction. So that's why the best thing you could do for your system is install the deepest filter you can, which would be, in this case, the 4-inch filter. It's less pressure drop, it's more surface area for the air to go through. So basically it doesn't just deadhead against the filter and get disrupted that way. It's easier on the equipment and it's easier to filter that way. Yeah, there's a dirty filter, clean filter. That's really not even the worst you'll usually see. Again, it's like, most of the times you find it in like topsoil ready condition. You know, it's been in there for like years.
I have a filter?
Yeah. So this will kind of go.
If MERV 13s are the best.
MERV 13s are not the best. We'll go through this chart here. That's a good question. So this will show the MERV rating. The lower it is, the less particulate size it can filter out. Or sorry, the lower the filter rating is, the MERV rating, the larger the particulate size is that it filters out. So a 1 to 4 can do things like dust mites, sanding dust, let's see, other ones they run into, carpet fibers. And then if you go all the way down on the opposite end of the scale to like a 17 to 20, a MERV 17 to 20, you're below 0.3 microns for the particulate size, and that can catch like viruses, carbon dust, sea salt, like really, really fine things. And so yeah, you'll find those in they say pharmaceutical manufacturing, clean rooms. Clean rooms are the big one. So the higher the MERV rating, and on this it goes up to 20, the smaller particulates it can filter out. On that note though, not all equipment can handle a really, really high efficiency filter. And the reason for that is they're very, very restrictive of airflow. So if your fan motor, if the equipment wasn't designed to overcome that obstruction, then you're not going to be able to move the amount of air that the system needs. The fan motor will overheat, won't keep up. You'll run into all kinds of issues. You'll see these pad filters a lot. Those would be on like the low end of the scale. I mean, you could like pour sand and it'll come out the bottom of it, right? Like they'll catch the big stuff, but I mean, it ain't much. Let's see, and then you do run into electronic style filters. Really, you'll see a ton of them out there. Do you have any specific questions on filters, if you run across anything? When I did residential, we did have people who had issues with like they were really, really hypersensitive to dust, things like that. They actually had a separate filtration system aside from their furnace. They had their own fan with its own like HEPA filter and its own ductwork. That whole system's only job was to filter the air in the home. Because like I was saying, when you get to these really high efficiencies, most of your equipment isn't designed to handle that. And that's why like we will install a maximum MERV 13 on most equipment. You're kind of finding that balance between quality and then what the equipment could do. You could throw a MERV 20 into like your standard gas pack, but now we're going to be coming out because in the air conditioning season, your coil's icing up.
Yeah.
Or now we're not moving the same amount of air through the system, so things are uncomfortable. So it's kind of just really finding that balance between the two. Does that answer it? Do they have anything else? I can feel my phone going off.
No. I put in some color commentary there about the best that your system can handle.
Yeah,
Actually, Janice.
that's a good way to put it.
Janice does have a question, it looks like.
Yeah.
She might ask you to.
If your tenant says, we only want a filter that is what is it for virus? The CDC or whatever it is approved. They don't want to have the best
Yeah.
virus. What's CDC or whatever it is? What's the health approved MERV filter? Do you know which one it might, what level? I assume it's.
Well, like New York and Los Angeles right now have mandates that public spaces have a MERV 13.
Oof.
So, but it depends on, like Joe said, your system and what static it can handle. But note that you're not stopping a virus until you get into that 17 to 20 MERV rating. And there's very, very few systems that can handle that. They're purpose built. So what you're doing with that higher MERV filter is you're providing cleaner air inside the space, which equals good housekeeping and less places for a virus or bacteria to hide.
Mm-hmm.
You're not assuming that virus is traveling up through the return through your system and then being caught by the filter. We've seen zero proof of that in studies. It's providing cleaner air inside the occupied space.
So we can assume there's no CDC standard for us on a package unit, correct?
No, they say to increase filtration, they say and generally we refer to what's called ASHRAE, the American Society of Heating and Refrigeration Engineers, and they provide guidance on filtration, indoor air quality, and their recommendation is the best filter that your system can handle.
Thank you.
Now, there's other recommendations too, such as building flush, increased runtime, recommissioning and rebalancing, and making sure that your system operates to the best of its abilities. But there's no mandate that says you have to install a filter that your system cannot handle.
Yeah. Cool. All right, does that answer that?
Perfect. Perfect. Thank you.
All right. Cool. Yeah, you're welcome. Cool. So now we're going to talk about RTU, rooftop unit. This is basically like a giant gas pack. They don't always have to be gas, but sometimes we hear me say gas pack. This will be a rooftop unit. You'll see these, they'll be like looking like a box car up on top of a roof. And for the most part, and I'll show you in the next slides, this would be that central plant situation, and I'll kind of get to why. But again, you'll see all the components. There's the relief fan that can relieve air from the space. You have your economizer, you have the evaporator coil, filters, you have your heat strips here. This one is actually electric. You have your fan, and then you have the condenser section. But now it's just getting really big. So installing a bunch of smaller rooftop units, like those little gas packs we were showing earlier, you got one big one. So on here, when I was saying, and commercially, we'll have a combination of that whole central plant situation and unitary. You're going to have the top unit here. This is going to be a rooftop unit, and then it comes down to a bunch of these VAV terminal boxes. Do you have VAVs in any of your spaces?
I don't think so.
Okay. Well, this will show you. basically it's conditioning the air, bringing in outside air and supplying. Let's say it's just supplying 80-degree air here, or actually it's easier for cooling. Let's say it's supplying 50-degree air down that ductwork. Now, it'll get to each of these VAVs, and there will be typically a thermostat for each one of these, some kind of control, because each space is going to want its own temperature. So the spaces that want cooling, a damper will open up here and allow cooling into it. The spaces that want heating, that damper will close so we don't bring in that cool air, and then inside of that unit, it'll heat up the air to what it wants. Yep, so each box is its own zone. This would be an example of like a multi-zone system. This is a pretty common setup. And then we'll show you, did we have one of these boxes? I think we do. In the lab, we can show you after this, in the lab, we got a bunch of this equipment out there, like VAVs, and you can see it on a small scale and see it. But this is a type of VAV, it's called a squeeze box, and it's used on the interior zones where you don't need heat. Like the space just stays warm, so it doesn't have that supplemental electric heat on it. So this, all it does is if that space wants cooling, it'll open up the damper and let that cool air come through that's being supplied from the rooftop unit. So there won't be a filter on it. There's not going to be electric heat. It just opens up, cool air in.
Kind of like a bypass almost.
Yeah, I mean, essentially. And then this is your most common VAV. So again, it's like its own little system. It's going to be that unitary, zone driven. It just cares about one zone, has the thermostat. On this one, it has a hot water coil on it to raise the temperature of the air if it wants to do that. And then there's going to be on the return air here, typically cold air being supplied to it. So if you want cooling, water valve shuts, you don't have hot water going through, this damper will open and let cold air through, and then it goes and supplies the space. If you want heating, that damper shuts, that hot water starts going through the coil, and we actually close off that damper, but then you'll have over here a filter and another damper that opens up, and we bring in air from the space, heats it up, and supplies it. So that's kind of the most common thing you're going to see. Again, you don't have VAVs, but we'll show you. It'll make sense. Maybe you even have seen them.
I've seen them before.
Yeah, okay.
We just don't have them at these buildings.
Yeah. You mainly like hydronic units, that kind of thing?
Yeah.
Yeah.
Heat pumps.
Cool. So that's actually going to be the end of it. We're going to go through the review process. So why some buildings perform better than others. That was that very first thing we talked about. From your understanding, why do you think some buildings would work well and some wouldn't?
Well,
And it kind of
depends
Yeah.
on a lot of stuff.
Maintenance.
Maintenance for sure. But yeah, kind of what we're trying to get at is that it kind of comes back to the purpose. Was your building being used for the purpose it was designed, right? Like I was talking about the building I have that used to be just office spaces and a lab has moved in.
Yeah.
I mean, granted, this lab is now like changing out half of the place and making it work better and installing new equipment. But typically it's, are you using the building for what it was intended for? Yeah. But maintenance too, yeah, absolutely. If you got the whole what filter situation and nothing's been, half the stuff doesn't work, then yeah, it's not gonna work that way. And then why we get complaints during weather extremes, and that was because we don't design the equipment for weather extremes. We can, but
It's not
It's
cost
not.
effective.
yeah, it's not cost effective. Now you kind of know what a zone is. It's a thermostat that's controlling one room or one space that you want to heat or cool to a certain spot. Difference between a split and package system. Again, I think desktop computer versus laptop, that's the easiest way. And then the drawbacks of that too, I was thinking, how could you explain to someone how hard it is to install a split system sometimes? And I would say, go put part of your computer across that, go put it across the building. And now go put the monitor in another spot in the building. Now here's a cable, connect them, make it look good, run it the way you want it, and you'll start seeing like why that would be kind of a thing. Why positive building pressure is important, how it's maintained. So again, there's that picture. It's a little hard to see here, but the dirt rings, you want positive building pressure. So the air you are bringing into the space, you're controlling where it's coming from, you're heating or cooling it, you're filtering it, and you can control it that way. Because otherwise, it's going to creep, right? Yeah, and that's pretty much the end of it. And then you already talked about, Seth, the classes that are coming up, but just to reiterate, our next class is going to be the part 2, right?
Yeah, part 2.
Yep. And what is the date for that in their handouts?
22nd?
22nd, yeah, it's the 4th Tuesday, so all Seattle classes and the teams are the 4th Tuesday of the month at 1:30 p.m. Pacific. I didn't realize I had to specify Pacific time because we had some.
Oh,
people
yeah, remote.
Outside the time zone, so that
Yeah.
was my fault. I didn't think that far ahead.
Yeah. And then, yeah, I kind of opened it up at this point. If you got like more questions of what we covered, or if you got other questions in general, you know, pretty much try to get to that. But just keep in mind, if we'll likely have a class on specifically that system to go, you know, deeper in. So don't worry if we didn't get to everything.
Good.
Yeah. I don't know, anybody on the teams have any more questions?
Not at the moment, at least in the chat.
Yeah.
I do have a survey I'm gonna put in here for,
Oh, yeah.
for these. We have them in here too, but I'm gonna see if I can attach it here.
Hope you didn't print a lot of them.
Yeah, feel free to take like 10 sandwiches, a couple cups of macaroni.
Oh, I will. I think we're good. Got a few minutes left, but we did good on time. Let's see if I can get this survey going up. That's good.
I had to do so much to get here, so I'm glad you guys have some food.
What buildings are you at? Are you downtown? Are you Seattle mainly?
So I've
Okay,
moved
well,
around
thanks.
3
Say
times.
Say goodbye.
Yeah, thanks.
I
Yeah.
appreciate you coming in.
Thank you, everybody.